All right, so today we're looking at applications. And applications is exam 2, probably something along the line. So, differential equations have applications in business and science. Alright, so differential equations are about change and how things are changing, so therefore anything which involves a situation where stuff's changing you could simulate with differential equations, so business and science. So two scientific applications, I'll give you a couple of examples. Alright, so the first one's what's called Newton's law of cooling. And that relates to the rate of cooling of or the temperature of something over time. So it relates the rate of cooling to the current temperature. And the temperature of the surroundings. Alright, so what it is this. So differential part. It's big T, little t. Big T is temperature, little t is time. So the derivative of the temperature with time, so the rate that the temperature is changing with time, and it's equal to some constant, and also the other is the temperature of the thing at the time and the temperature of the surrounds. Alright, so this is, excuse me, this is the differential equation of Newton's law of cooling. So that's one example of, in this case, scientific application. I'll give you another one in a minute of how a differential equation can be used in science. Alright, I'm right to rub that off.
So K is just a constant?
K is a constant, yeah. And it's probably relates to, what the substance is, probably, and other things as well. But for a particular material, that K will be constant. It might be different value for water or lead or aluminium or whatever. Alright, but it is constant. Alright. So the other one that we can use for as a differential equation is radioactive decay. So those of us who are doing physics will know about half-lives and radioactive decay. Basically, for radioactive decay, there's another way of looking at it as well. So we looked at the half-life, where it halves every whatever period the half-life, of 4 hours, then the amount of substance halves every 4 hours. But there is another way, differential equation. In the differential equation you can find, at any time. So the rate at which radioactive substance decays is proportional to the mass that's there, the mass remaining. All right, and as a differential equation, the rate that the mass is changing with time is proportional to, so equals K. So whenever something's proportional to, all right, so proportional to, whenever you see that, whenever you see something that's written and it says that it's proportional to, it equals some constant times the mass remaining. So Km. All right, so they're just two examples of things that can be expressed by differential equations. All right. So, having said that, this first example is going to use another. I'll write that off. So populations of things might be another, and that's this first example. That's what we're going to be looking at, is the population. I'll get my piece of paper so I write it down correctly. So the population, P increases at a rate that is proportional to wherever the population at the time. Find the expression. Population at any time. All right, so first of all we're going to write the sum. So population increases at a rate. So if the population, and then we've got time down here. So whenever we see rate, we think differential equation, and it's the population, and it's time. All right, the next bit that says here, it says proportional to. So whenever we, proportional to is this little alpha, proportional to. But when we, as I already mentioned, when we go and do the sum, we replace that by equals k. And what is it proportional to? Well, it's the third bit, the square root of the population. So the square root of the population. Oops, and I'll leave that up here as well. All right, so there's our differential equation. We've now got to solve that. So, first technique we're going to do is flip. Yep. All right, because this population over here, so we need to differentiate with respect to population. So we've got to flip. So 1 on k root p. All right, how are we going to rewrite that then?
T is equal to the antiderivative of
Antiderivative. We've got 1 over this root p.
p to the negative r.
Negative a half, yep. So t to p. 1 over k. P to the negative half. So then when we anti-differentiate, as already been suggested, the k is a constant, so we can put that out the front there like so. And then we are anti-differentiating p to the negative a half with respect to p. So if I am correct, that means that we should have increase the power by 1, so it'll be a half, divide by the new power. Oops. I'll put 1 on 2 there, it should be 1 on k, plus some constant. So neaten that up. Dividing by a fraction, turn it upside down and multiply, so we've got 2 on k times p to the half plus some constant. All right. Now the question says find the expression for the population at any time t. So that means we need to have the equation written as
Any.
p equals, yeah?
Oh, yeah.
Yeah, p. So find the expression for the population, p equals. At any time t, well, all that means is there's going to be t in the equation, isn't there? Yep. All right, so let's add, or take our constant, I should say, plus that equals 2 on k, p to the half, 2 on k, times both sides by k on 2, is p to the half, and to get rid of the half, what do we do?
Right.
Yep. So there's an expression for the population at any time t, and to find out what the k is and the c is, we would need, excuse me, we would need information. All right, anything about that one? No? All right, next one. All right, this next one we're using Newton's law of cooling. All right, so an iron bar placed in a room which has a temperature of 20 degrees Celsius. Excuse me, the iron bar initially has a temperature of 80 degrees Celsius. It cools to 70 degrees in 5 minutes. So find part A, find the temperature at any time. And part B is how long does it take to cool to 40 degrees Celsius. 40, not 4. All right. So here we've got a room, which is temperature 20, so that's our surroundings.
I'm sorry to interrupt you. I know you said it was but it's not a double. So just clearly, I'm trying to find somewhere to for a double for you. So, in my view, is that okay?
All right. So there's our surrounds. We've got 2 lots of information. We've got that it's initially at 80, and the other bit of information we've got is that it cools to 70 in 5 minutes. All right, so if it's a cooling thing, we're using Newton's law of cooling. So that means that the temperature dt, temperature d time, is equal to k T minus Ts. Now sometimes, because it's cooling down, it's going down, so sometimes you'll see people write this initially with a minus here. Whether you put the minus there or whether you don't, in the end, it doesn't make any difference. Because when you do your calculations to find what this constant is, it takes care of it. So that's not something you need to stress, be worried about. So let's put in our information. We know the temperature at any time is K times in whatever the temperature is, minus the surroundings, which is 20 in this case. All right, again, we've got the same situations we had in the previous example, and is that our variable is temperature, and temperature's on the top, so I'm going to flip it. Oops. So it's 1 over all that stuff. Close the bracket. All right, then time, constant out. What do I get when I anti-differentiate? 1 over t minus 20. Anti-differentiate 1 over, it becomes log, yep. 1 on k, log to the base e, t minus 20, plus some constant. All right. So now we've got 2 bits of information. So here's our thing. Before I go rearranging to find the temperature at any time, I'm going to use these bits of information because I've got 2 constants, k and c, and I'm going to try and find out what they are. So I've got 2 bits of information. It's initially, I need 5 minutes. So when t equals 0, the temperature was 80. So we'll put in that information. Okay. 80 minus 20 is 60, of course, and then we can take that stuff from both sides. So C would be 81 on K, log to the base E of 60. All right, happy with that? All right, so when we put that in, should I skip steps or not?
No.
No? All right. I won't skip steps then. So, that means that I can now put this here. So I've got T equals 1 on K, log to the base E, T minus 20, minus 1 on K, log to the base E of 60. 1 on K is a constant. That's a common factor. Yes?
Yeah.
And then I've got log minus log, and when I go log minus log, we divide. So we've got that. All right. So we've used one piece of information, but we've still got a constant we don't know, but what we do know, which I've rubbed out, is when T is 5, the temperature is 7. So by just doing that and saying T is 5, I've already, time in this particular case is in minutes. All right, we weren't told that we had to have it in seconds or anything like that, so we can please ourselves. All right, so 5 is equal to 1 on K, log to the base C of T minus 20 over 60. So K is 1/5 log to the base E, t minus 20 on 60. And then we can stick that in. Right, so there's a fair bit of, in questions like this, there's a fair bit of manipulation, algebraic stuff that we're going to have to do, so you have to be patient. So, let's stick that in then. So t equals...
Do you substitute the 70 in for t?
I forgot that, didn't I? I forgot 70. Put that in up there, thank you. That makes a difference, doesn't it? 70, and that's 50 on 60. Or 5 on 6, if you like, which is what I'm going to write here. All right, so where are we? 1 on k. So 1 on k. So if that's k, it's probably not a very good way of writing it. It's probably going to be better if we write it like this. Because when we do 1 on, we're going to have to flip it, aren't we? So t equals, it'll now be the 5 on the top. And then log to the base e, t minus 20 over 60. And there we go. All right, now we're going to have to do a whole bunch.
Wait, why did you flip it, sorry?
Because he's
that's...
1 on k.
Okay.
1 on k here.
Yeah.
Yeah, that's why I flipped it. All right, now there's a whole heap of rearrangement that we're going to have to do. All right, so divide by 5. Then times both sides by log to the base e of 5/6. So we've got t on 5 times by log to the base e of 5/6 equals log to the base e of t minus 20 over 60. Log law. Come up there as power, yeah? Because what that then allows us to do is we've now got log to the base e of something on both sides, haven't we? Log to the base e of this stuff, log to the base e of that stuff, and so what that means then, over here, is that 5/6 to the power of t on 5 has got to equal to temperature minus 20 over 60. And the last bit, times by 60. Add 20. And is our temperature at any time, so a bit more complicated. Anything about any of that? It's quite a long process, so you've got to be patient and not try and...
So would this be in the second exam?
This type of question, but it would be broken up into
But
bits.
you wouldn't want to, would you want to spend this much time working that out?
Well, like I said, it would be broken up.
Right. But would you put it in your calculator or?
Well, you'd have to be guided by how much marks and space. So to do this by hand, you need to be given a lot of space.
But they wouldn't do that because it's a calculator exam.
Because it's a calculator exam, it's unlikely that they're going to, yes.
Yeah, right.
So you would probably find some bits, and then this bit would probably you use your calculator to get your calculator to do the rearranging. Which you simply do, you just go solve that for bit 2, and then your calculator will do the rearranging. All right. And part B says what time when t equals 40. All right, and so that's 40 equals 20 plus 60, 5/6 to the t on 5. By hand, there's a whole bunch of stuff. So, calculator, your solve function. For that, it's really to do when t is 40. It really makes more sense to use this one up here before we rearranged it. Because if you stick it in there, you've got to rearrange it again. All right. So, yes, don't forget, calculate solve, and when you do that, you get that the time is 30.128 minutes. All right. Okay, so there's one other thing that I'm just going to define for you. And that is if we have a difference in rates. Difference in rates. So there are situations where there might be an increase as well as a decrease. So like population of a city, for example, you might have people moving in and people moving out. So there's an increase and a decrease.
Right,
So,
no worries, thanks.
So you need to, put that increase and decrease together. So in many situations, So I already gave you one example. Another example would be, say, water flowing in. Into a tank, as well as flowing out. Right, so something like that. So you get water coming in, so the rate's increasing, or volume's increasing, the rate of the volume's increasing, and then there's some getting taken out. So there's a decrease. So the way we deal with that is we look at the overall, the rate of change. And so the rate of change, right, so that's the overall of what's going on. We usually define it as the rate of increase minus the rate of decrease. So, before we finish that, I'm just going to write up the question, and then we're just going to set up the differential equation. I'm not going to solve it, we're going to set up the differential equation for this difference in rates situation. All right, can I write all that off? Yes, no, maybe. Alright, so for example, here's the situation, a radioactive substance. Decays at a rate of 2m per year. And because we do physics, we know with the decay chain, it's often things decay into something, then something else, and so on. So this particular radioactive substance, in this case, is having something above it in that chain decaying. So the isotope is formed substance, isotope, you haven't used the substance, use that, just I've used it above. By a product a nuclear reactor at a constant rate of 0.5 kilogram per year. Alright, so set up the differential equation. For this situation. All right. So when we look at this, we're saying it decays. All right, so that's our, if it's decaying, it's reducing. So that's our rate of decrease. And you'll notice that this time it doesn't say it's proportional to anything, it just says it is. It decays at this rate. So when then it's 2m. Alright, it doesn't say proportional, so there's no k in there, it just says at this rate, at 2m, so
So
it equals 2m.
if it was proportional, we'd put K in as well.
Somebody's figured that out for us, yep. It's proportional to something and someone's done the figuring out and this is what the rate is. And the increase, we need the increase, and so it's formed, so that would be increasing, and it says here at a constant rate of 0.5. So our rate of increase is 0.5. And so we're asked to set up the equation. So the equation, the mass that it changes with time. Okay, rule of thumb is we go increase minus decrease. So in this case it's 0.5 minus 2m. And then if we were asked to, we would go ahead and solve that equation. All right, so any questions about that before we stop?